Actually, could have taken this off here. So, yeah, let's continue. We want to calculate the emission phase. Yeah, so this is how I called it, or the atomic phase. And maybe this slide here, so the title page of this thing here. So maybe I should explain this, right? So it looks a little bit, yeah, so you could ask questions. So this is actually the zoom in of this photo, which is from, well, which is more than 20 years old, almost 25 years old. You see me here at a young age, and even younger, my former PhD students, Felix Zacher and Felix Grasborn. And what you see here was that the first time that we were able to record high harmonics, right? And this was a little bit difficult because we did it in a way that was very unusual at that time. Well, it probably still is. We had a laser with a very high repetition rate, but with a very low pulse energy. At that time, at 100 kilohertz, the maximum you would get would be something like 4 microjoules, right? So everybody would do it with at least 1,000 times higher pulse energy. And we dared to do it in a way where at that time everybody said, well, it will never work. But it did work, right? And only later, in particular the group in which Robert Klaas works, the dissertation I just cited, so a group of Jan Rothart, Jens Limbert, they really understood why we were able to measure that, right? So we got much more harmonics than we expected at that time. Okay, anyway, so that's here. Let's go back to the script here. So we want to compute the atomic phase. Yeah? So we said that at different intensities, and we are necessarily producing harmonics at different intensities because we are in a Gaussian focus. Yeah, so at different intensities, a given harmonic has as an underlying different trajectories, right? So if you're at a position in the focus where the intensity is low, then you probably need a trajectory that produces harmonics in the cutoff region, right? And if you're at an intensity that's high, then of course you have a different trajectory. You don't have a cutoff trajectory. You produce, you're locally somewhere in the plateau, whereas with your harmonic, whereas at lower intensity, you're close to the cutoff, right? And of course, if the intensity is too low, you're not able to produce the harmonic, but that's clear anyway. Of course, the higher intensity is in the focus, but of course, we not just want to produce, so let's go to this, back to this picture here. We not just want to produce the harmonics in the very high, at the very highest intensity. We want to produce them in a volume as big as possible in order to get a lot of output, right? So in nonlinear optics, it's the same thing, right? There, in my course, I calculated at some point the efficiency of second harmonic generation, right? And there we do a much simpler thing, yeah. But basically, it's also the case that we want to use as much volume of the crystal in order to produce the second harmonic, right? If we would restrict ourselves to the highest intensity here, we wouldn't get much. Okay. So computing the atomic phase. So what we need to do is to analyze the situation between T0 and T1, between the birth of the electron and the recombination. But of course, also before the birth of the electron, so because the birth time varies with the type of trajectory you have, you also have to take into account these things. Right? So after recombination can be a little bit earlier or a little bit later, depending on which type of trajectory or which trajectory you have. So if you return earlier, then of course you emit the harmonic earlier, and a certain phase is picked up just because of this argument of a wave, right? Omega t times omega t minus k times z, right? So one needs to consider these things. So let's write it up. I hope it becomes then even clearer. So in order to compute the atomic phase, we need to analyze the processes between the birth T0 of a trajectory and its recombination. At t equals T1. Yeah? And now, if we talk about trajectories that are relevant for high harmonic generation, the difference between T1 and T0 is always smaller than the optical period, right? So this means that we can restrict ourselves to one optical period. Yeah, so we have to take stock of what happens in terms of phase evolution in one optical cycle. Yeah? So for trajectories relevant for high harmonic generation, T1 minus T0 is smaller than capital T, yeah, so the optical period, which means we just need to take stock of the phases accumulated in this optical cycle, yeah, in this optical cycle. So the idea is kind of, from the screen we follow our ray back to the voxel, and then we say we afford an additional optical cycle, and we look at which phases develop there. Yeah? Okay, well, and these are three things. Yeah? So when t is between 0 and t0, right? Then we have the evolution of the ground state, right? In the ground state, the phase evolves according to the binding energy divided by h bar, right? So the ground state energy is EIP, right? And this means that we get phi 1 equals EIP. And now the time that we have, yes, T is 0 minus 0 divided by h bar, right? Of course, I could also take 2 cycles, right? Then instead of 0, I would have here something else. But this would just add a constant phase term to all trajectories, to all rays. Sorry. Okay, so this is the first point here. The next point is what happens between T0 and T1. Yeah, so this is the interesting stuff. Yeah, so there the phase, the accumulated phase, is given by the classical action of the trajectory. Yeah, so people always say classical action of the trajectory. Actually, I don't know a quantum action. Yeah, so it's always the integral over the Lagrange function. Yeah, so this is the so-called classical action. The classical action. So this is what Matthias used in order to calculate interference in strong field laser physics. Right? So this action, this is the integral of the Lagrange function for this trajectory. Yeah, so classical action. Yeah, let me put it in brackets. So yeah, and then the rest, right? So after the emission, there the phase that accumulates, so phi 3, I would call it, is q times h bar omega times, well, the time that's available for that, namely capital T minus T1. Yeah, so at T1, the photon is emitted. Yeah, the photon h bar omega is emitted. Which means we need to take into account its phase evolution, so the phase evolution of the photon. It's given by q times h bar omega. Yeah, and what we see is the only non-trivial part is the action. Yeah? So the only non-trivial part is the action S. And of course, yeah, so that's apparent also from above. And T0 and T1, yeah? Yeah, so they change as we change the trajectory, as we use a different, or as we need to use a different trajectory in order to generate a given harmonic. So, how do we do that? Yeah, so I need a new page for that. A familiar figure. I hope you have, yeah, I'm pretty sure you have seen it. You must have seen it. So here we have a figure where we plot, so in red, we plot the return energy of a trajectory that is emitted at a time t0, right? Yeah, so we have a quarter of a cycle, so this is this cycle where the trajectories return. And you see, here you see the 3.17 UP for the cutoff harmonic. Yeah, so everybody knows this curve, right? Do you also know this curve here, which is the classical action? Not so well. Yeah? maybe Matthias didn't introduce this. But of course, you can calculate for each trajectory, we can calculate this thing here. Yeah? You just take the integral over the Lagrange function for this trajectory. Yeah? So you just calculate this numerically, and you get this thing here. Right? And this is the phase. This is the phase in radians, I guess. I wrote here atomic units, but this is probably wrong. So now the interesting point is that this figure is sufficient to do the entire calculation, the entire non-trivial part. Yeah, so because what I said is the only thing that we need is the classical action for the trajectory that we want to use. So let's see how this works. So assume, well, we use the figure to determine S. Yeah? And in how many steps? In 4 steps. So the first step is a trivial one. We compute the energy of the photon, Q times h bar omega, in units of UP. Yeah, so all of that stuff is scaled. Yeah? We compute the energy of Q times h bar omega in units of UP. Yeah? And then if we have that, we can determine the time t0 of the trajectories, right? And how do we do that? What we do is that we draw a horizontal line, say this here, say this here is Q times h bar omega, Q times h bar omega, right? Okay, let's write that down. Yeah, so draw a horizontal line at Q times h bar omega. Yeah? Then the point is that we just need to look here, right? And we get the T0. Right, so this is actually the T0 for the long trajectory. We see that for each harmonic energy, there are actually 2 trajectories. Only for the cutoff trajectory, there is just 1. Right, so this here would be the T0 for the short trajectory. I can say right away that the short trajectory is the more interesting one for high harmonic generation, because it turns out that this trajectory is favorable for phase matching. Okay, yeah. So this would be already the third point here. The intersection of this red curve, the intersection of E1 of T0 with this green one with Q times H bar omega yields the T0 for the long and short trajectory. Yeah, so each harmonic order can be produced by two trajectories in each voxel and short trajectory. Yeah, and they are called T0 long and T0 short. Yeah, and now we are already done actually. Yeah, so now we just need to take this intersection here. Yeah, so these points here on this blue curve here, they provide the S. Yeah? And because we plotted here everything in terms of UP, yeah, so everything, the energy and the action, they are proportional to UP. So this must be arbitrary units here. Yeah? They are proportional to UP, therefore I know everything that needs to be known. Yeah? So I know just from this scaled interaction, I can determine, so just with this graphical method, or if you have tabulated these values, you know everything that you need to know. Yeah? Okay, so the final point. So the intersections of, well, this yellow line with S of T0, which is actually blue. So let's make it very pedagogical and use a lot of colors. So the interaction of this of these yellow lines with S of T0 yields the actions for long and short trajectory. We call them S long and S short. Good. Yeah. And just to point that out once more, so this figure can be used for all voxels because it is scaled to UP. Yeah? So the figure or this method and the procedure above can be used for all voxels because E1 is proportional to UP and S is also proportional to UP. Yeah? We just can scale it. We can scale the figure. Well, the figure is already scaled. Yeah? We can scale E1 and S by UP. Yeah? So S, the action, also scales with UP. Good. Yeah, so let's see what comes out. Yeah, so the discussion is actually a little bit tricky. Because we have this this focus with all the different intensities, and we need to look at the same harmonic at different intensities. Yeah? Okay, so here you see something that's familiar. So this was the red curve in my case. So these are figures I took from the diploma thesis of Wolfgang Stremme. Well, this is wrong here. This was not in 2021. This was in 2002 or so. Yeah, so it was in 2002 when I was still in Munich, or 2001. I don't remember exactly. Okay, anyway. Here the same thing plotted now, not as a function of t0, but as a function of t1 minus t0, which is called here tau, right? So it's kind of the travel time of the trajectory, right? And what you see now here, now it's a little bit more complicated, right? So we have now different intensities, like in a focus, yeah? So this here is the intensity scale. So in this case, we go from a little bit below 10 to the 14 watts per square centimeter up to maybe 3.5 or so watts per square centimeter, right? And the contour lines here, they are for a given harmonic, right? The highest harmonics, they need the highest energy. Yeah? So this is for a given harmonic, the intensity where the cutoff is. Yeah? So for higher intensities, you can produce the this harmonic either with the short trajectory, yeah, so the smaller travel times, or with the long trajectory. At the cutoff, there's only one trajectory. Yeah? They are both trajectories converge to one, right? And beyond that, there's nothing, right? And of course, the lower the harmonic, the lower the intensity at which you can produce them. Yeah? So nothing in particular. Okay. Yeah, so they represent the harmonics. Yeah, so these contour lines, as I said, they represent the harmonics. I don't know now which harmonic this is specifically. Say this is the 13th harmonic. Then this would be the 15th, 17th, 19th, and so on and so forth. Right? And the higher the order, the more intensity you need, even for the cutoff. Okay. Yeah? Okay. Yeah? So once again, this half is the short trajectories, corresponds to the short trajectories, and this here to the long trajectories. So now we put the result of this calculation that I just have shown you, we put on top of that. So what you see here in colors are the phases computed by this method, right? And now if you follow a certain contour line, yeah? So what you do here basically is that you, if you go along this line, right, then you follow a certain harmonic through different intensities, right? And what you see here is, well, that not much changes with the atomic phase here. Yeah? So basically, if you follow this here, it's all the time the same phase. Yeah? This looks nice. Yeah? Same thing here for the next higher harmonic. Right? So you see that there is a phase gradient in this direction, but we are only interested in how the phase changes if I change the intensity for a given harmonic. Given harmonic means that I follow a contour line, right? And you see that it's fairly flat. Well, what you also see is that it's not so flat for the long trajectory, quite in the contrary, right? So if you follow it for the long trajectory, then there is actually a pretty, well, a significant phase gradient for the long trajectories. Well, it's kind of not so surprising, yeah, because the longer the trajectory, the more action you would pick up. Yeah? So it's not an entire, it's not a complete surprise. Yeah. So and what's plotted here is actually just what I said. Yeah? So say for the 25th harmonic. Yeah? So assume that this line here would be the 25th harmonic. Yeah? And we follow that here, right? And plot it as a function of intensity. Then we get, for example, this, so this curve that's highlighted in green. Right? And one can just fit a line to the two branches here. So this is the flat one. This is for this part here. And the steep one here is for this part. Right? And here in the middle it does something funny. Yeah? Yeah? So we have the slopes here now for the long trajectory and for the short trajectory. Right? You see that this slope is fairly low. Good. Yeah? Understood how this works? So now next thing. So now instead of plotting it versus intensity, we map it to a focus. Yeah? In order to start, we just go along the z-axis, and we just follow what happens there. Yeah? So this here is for the in the focus the intensity gets higher, right? And we just use the mapping of intensity on focus, and now we map it on coordinate instead of intensity, right? And you see a fairly flat behavior, and here for the long trajectory a steep behavior. What's also plotted here is the GUI phase, I should say. He's a Frenchman. And we need to add both in order to get the total phase, right? And what you see here is that behind the focus, yeah, the GUI phase, the GUI phase has this slope, has a negative slope, and the emission phase, the atomic phase, has a positive slope, right? So here they compensate each other. Here it gets flat, right? So here you find actually the sum of both, of GUI phase and we need new batteries. Yeah. Well, according to this, it's still okay. Is it fine again? Very good. Okay, so once again, for this figure, I add the black curve to the orange curve in order to get this new orange curve. Right? It looks pretty much the same as the GUI phase, but actually it's not, right? Because you see, it doesn't go through the origin here, right? And well, for the green one, for the long trajectory, both curves, green curves, looks very similar because the phase, the accumulated phase for the long trajectory is much larger than the GUI phase. Yeah, well, highlighted here. Yo.
Why is the GUI phase going from like 10 pi to minus 10 pi? Why is it like not being higher if I would do
Good question. I never noticed that. That's obviously wrong. So this is a different scale for both. Yeah. Okay, thanks for that remark. Okay, now we do this for the entire focus, right? So far we just took a cut through the focus here, right? This is what we had so far, but now we we map out the entire Gaussian focus, and we would look where the phase gradient is small, right? Once again, after all, we talk about phase matching, right? Meaning that the phase mismatch, so the gradient of delta k should be equal to 0. And what you see here is, so the beam goes in this. I'm afraid that this is actually not. Oh yeah, so this is the beam direction. And what you see is that, well, I'm not sure whether this beam direction, I'm not sure about the colors here. In any case, you see a settle point here, right? And this is where we have phase matching. And if this should be behind the focus, and therefore I would guess that the beam direction is plotted here wrong, right? So it should be behind the focus, right? If we look at the long trajectory, then there are also settle points, but it's actually not a settle point there or a certain volume, but it's actually a ring here. So we have here cross sections through the focus, and it's easier to see here because the phase gradient is larger, right? Therefore the colors are more different. So we see that that there's an extremum here, and you have to think about that this is, of course, has rotational symmetry. So it's a ring here, right? So what you can guess from this figure is that actually the emission characteristics for the long and for the short trajectory, they are quite different, right? And what one can, well, I think, I'm not sure on how to interpret the colors. So the flat region must be here behind, and here it's before the focus. And therefore, by moving, so if you have a sufficiently large focus, with enough laser pulse energy, you can actually move the gas, more gas density to, say, before the focus, and then you get harmonics from the long trajectory, and they have a different beam profile than when you move the gas jet a little bit behind the focal position, right? And people have observed this in the 90s. So the group by Pascal Sallier, Anne Lullier, and others, they found out these things. Okay, well, we don't have much time left. Now the question is what I quickly do. Well, there's one thing that's obvious, and I think we don't write it down, I just explain it. You know, the different harmonics come at different times, right? So we have seen that the higher the energy, the higher the energy, the closer for the short trajectory. So let's only consider short trajectories. Well, I think I need the graphical method once again. So let's see whether I find it quickly. Yeah, this one here. Yeah, so you remember the graphical method, right? if I have the no. Yeah, so if this here is the electric field, or integration twice of the electric field, right? Then if we take here the tangent, then we get the return time here, right? And we would need to move, if we have the short trajectories, these are points here, right? And it is clear that I get higher and higher energy, return energy if I move in this direction, because I move in direction of the cutoff, right? And now, the earlier I create a trajectory, the later it comes back, yeah? Or in other words, the higher the return energy, the later it is emitted. Yeah? This means that if we consider these harmonics attosecond pulses, that we have an atto chirp. Yeah? So the higher the frequency, the higher, the later it is emitted. Yeah? I like to translate this into acoustics, like in nonlinear optics. So this creates a sound like hui. Yeah? So it starts at low frequencies and goes up to, so it's positively chirped. Yeah? So the harmonics are positively, or so the attosecond pulses are positively chirped. So this also comes out of that analysis. And finally, one decisive point, and it's nicely pointed out in Robert Klaas' thesis, we have, one of the limiting factors of high harmonic generation is not only phase matching, but it is also reabsorption. Yeah? So after all, we generate XUV radiation with a quite high photon energy. So photon energy that's easily enough in order to ionize the medium. Yeah? And if it ionizes, if it photoionizes, the photon is gone. Right? So the absorption is actually quite high. And what I've plotted here, so from data from the Henke tables, is for 1 millibar, the absorption, right? So the D when the intensity of the harmonic or the radiation has dropped to 1 over E, right? And you see for CNOT it behaves like that, right? So the pink one is again the refractive index, right? And both curves are connected by the Kramers-Kronig relations. That's also clear, right? So here you see the same thing for xenon as, so it has a fairly high transmission. So this is what you get, well, this is what you get after this distance, right? And you see it looks very different for the different atoms. Yeah? So argon here, then neon here. So this is more boring. And so the boring curve is actually good for high harmonic generation, I would say. And here the same thing for helium. And it's clear that you can't, that it doesn't make sense to make your to generate harmonics in over a length that's large as compared to the absorption length, right? So it doesn't make sense to create harmonics here, and if you have a lot of gas, so that 90% of what you generate here doesn't come to the screen, right? So this is a limiting factor, and it's called the absorption limit. And has nicely been investigated by, as I said, by Robert Klaas in his thesis. Well, this is now a little bit too much to explain all of that, but basically you can understand it with the explanations I've given so far, right? And this here is a map of what has been done, so which efficiencies can be reached, right? So in different spectral regions, this is the so-called silicon window between, well, actually between 30 and 100 eV, I would draw it. And there the efficiency of high harmonic generation is fairly high, right? So 10 to the -7 or so. At even lower photon energies, it can go up to 10 to the -4 or even 10 to the -3. And the water window is another very interesting region, right? It's called water window because water is fairly transparent for this kind of radiation between, well, basically 300 and 500 or so eV. Water is fairly transparent. Yeah? Oxygen basically is transparent, but carbon is not. And then if you use this radiation in order to do imaging on a cell, yeah, then the water in the cell is transparent, but the structure, which is composed basically of carbon, also nitrogen a little bit and so on, you see this as a good contrast, right? This is why the water window is so important. And of course, this is also the reason why high harmonic generation in this window is interesting. Yeah, so the efficiencies are not very high, so in the order of 10 to the -9 so far. And well, it can be traced back to what we have done today, and of course in the previous lectures. Yeah, with this I would like to thank you for your attention. We are now at the end of this course. I hope you liked it, and maybe see you at a later instance. Yeah, thank you.